In this lecture, we'll define the radian measure of an angle. So far, we've been working with our angles in degrees. In degrees, we divide a circle into 360 equal parts. Each of these small parts of the circle is called an arc. 90 of these arcs is 1/4 of the circle, and that corresponds to an angle of 90 degrees. 180 of these arcs is half the circle, and that corresponds to an angle of 180 degrees, and so on. That means that an angle of 1 degree corresponds to an arc that's 1/360th of the circle. Degree measure works great for circles and triangles and our trigonometric tables because 360 is a large number with lots of divisors, so many of our angles can be expressed as simple whole number values that are easy to work with. But our next major topic in this course will be the graphing of the trigonometric functions. And when we graph these functions, we would like our input variable to be more general and not specifically interpreted as an angle. We would like it to not have units like degrees. So there's another way of measuring angles as a ratio that does not have units and will be more natural for these graphs. It'll be similar to the trigonometric ratios that we're graphing, and it'll be important in calculus when we study the derivatives of these functions. This is called the radian measure. In radians, we divide the circle into arcs of length equal to the radius of the circle. That means an angle of 1 radian corresponds to an arc equal to the radius of the circle. If we want to see what 1 radian looks like, we take a length equal to the radius of the circle, and we trace that length along the circumference of the circle. That arc will correspond to an angle with a radian measure of 1. A second arc of the same length equal to the radius will give us an angle with a radian measure of 2. A third arc will give us a radian measure of 3, 4, 5, and 6. And there's not enough circle left to fit another one of these arcs. That means that the radian measure of an angle that covers the entire circle is not going to be a nice whole number like 360 degrees. Next, we'll give the formal definition of the radian measure, and then we can compute exactly the radian measure of the entire circle and all of our standard angles. To give this formal definition, we start with a circle of any radius r, then we look at an arbitrary angle theta and its corresponding arc. The simplest definition for the radian measure of this angle is the ratio of the corresponding arc to the radius of the circle. This ratio will be constant for any fixed angle, because if we change the size of the circle, the arc length and the radius change proportionally. Another way of thinking of this is the number of times the radius of the circle fits into the corresponding arc. If we want to know how many times r goes into s, we simply divide s divided by r. Notice that in this diagram, the arc corresponding to the angle contains 1 full radius and approximately 1/4 of another radius. So the radian measure of this angle is approximately 1 1/4. And it doesn't matter how large or small the circle is, the arc length will always change proportionally to the radius. So this angle will always have a radian measure of 1 1/4. Let's look at an example where we use this definition. In this example, we have a circle of radius 12 centimeters, and we're told that an angle forms an arc of length 8 pi centimeters. To find the radian measure of this angle, we need to know the length of the arc and the radius of the circle, both of which are given in the problem. So we can substitute 8 pi centimeters for the arc length and 12 centimeters for the radius. Since these both have the same units, those will cancel out. And now we can divide top and bottom by 4 to simplify this, and we get that the radian measure of the angle is 2 pi over 3. To see what this means, we can look at a decimal approximation for this value. This is approximately 2.1. And recall from our previous diagram that 2 arcs of length equal to the radius takes us into quadrant 2. So this angle is just a little bit larger than that. It has an arc of length 2.1 times the radius of the circle. Also notice that in this definition, where we have a ratio of 2 lengths, the units cancel out. So that radian measure really has no units. It's simply a ratio or a proportionality constant that tells us how many times r goes into s. or s, as a multiple of r. Next, we'll use this definition to compute the radian measure of some of our standard angles. Here's our definition, and we'll start with a 360-degree angle. To compute the radian measure, we need to divide the length of the corresponding arc by the radius of the circle. For a 360-degree angle, the corresponding arc will be the entire circumference of the circle. And the formula for the circumference of a circle is equal to 2 pi r. So we can substitute that for the arc length. And when we divide by r, we can cancel the common factor. And this simplifies to 2 pi. So the radian measure for a 360-degree angle is equal to 2 pi. Let's think about what this means. 2 pi is approximately 6.28. Remember, pi is approximately 3.14. And the radian measure of the angle tells us how many times the radius of the circle fits into the arc corresponding to that angle. And for 360 degrees, that arc is the entire circle. Remember from our previous diagram, we saw that the radius of the circle fits a full 6 times along the circumference of the circle with a little bit left over. And that little bit will be approximately 0.28 times the radius. So 2 pi tells us the exact number of times that the radius of the circle fits along the circumference. Now let's look at 180 degrees. We could use an expression for half of the circumference of the circle for the arc length in this definition, or we could just use the fact that 180 degrees is half of 360 degrees, so its radian measure will be half of 2 pi, which is equal to pi. And pi is approximately 3.14, and that tells us how many times the radius fits in the half circle, a full 3 times, with a little fraction left over. That's approximately 0.14 times the radius. This is all related to how pi was originally discovered as a number. For at least 4,000 years, people have known that the number of times the diameter of a circle fits around its circumference is the same for all circles. They knew that the diameter fits a full 3 times with a little bit left over, and they could approximate this value as 3.14 or even more precise values. But it wasn't discovered until much later that the exact value of this was an irrational number, and pi is used to represent this value. So if the diameter fits pi times around the full circle, then the radius will fit pi times around the half circle, or twice that many times around the full circle. And the radian measure just says that the radius will fit a constant number of times into the arc corresponding to any angle, not just 360 degrees or 180 degrees. Now let's finish finding the radian value of all of our standard angles. So far we have the radian measure of 360 degrees is 2 pi, and the radian measure of 180 degrees is pi. Let's add to this 90 degrees and 270 degrees. 90 degrees is half of 180 degrees, so we get 1/2 of pi, or pi over 2, for the radian measure. 270 degrees is 3 times 90 degrees, so we get 3 times pi over 2, or 3 pi over 2, for its radian measure. Now let's complete our list with our 3 special angles. 60 degrees, that's 1/3 of 180 degrees, so the radian measure will be 1/3 of pi, or pi over 3. 45 degrees is 1/2 of 90 degrees, or 1/4 of 180 degrees. That gives us a radian measure of 1/4 of pi, or pi over 4. And 30 degrees is 1/6 of 180 degrees, so we get 1/6 of pi, or pi over 6, for its radian measure. When these are expressed in their exact values, as fractions or multiples of pi, they can seem rather abstract. But don't forget that they each have a numeric value that tells us how many times the radius of the circle fits inside the corresponding arc. Pi over 2, for example, is approximately 1.57. 3 pi over 2 is approximately 4.71. And if we superimpose our previous diagram here, we can see that 90 degrees gives us an arc that's approximately 1.57 times the radius, and 270 degrees gives us an arc that's approximately 4.71 times the radius. And you can do the same with the remaining angles as well. In our next lecture, we'll look at how to use conversion factors to convert between degrees and radians.